Pop the recording on. Howdy, folks. So it's good to see you all today. I'm using slightly different of a technology stack today, so I'd like, if anything goes wrong, please be patient. But I think nothing will go wrong, so we should be good today. I was just chatting with a couple of folks about the topic survey that was distributed in an announcement last week on Thursday. Right now I have, 32 responses out of 41 students in the class, which I think is really good. 75% turnout's great, but I would really recommend that you respond to this today, because by the end of day today, I'm going to pick the topic because I need time to prep the material and write up kind of a workbook and an assignment. So I need to do that, and it'll also be important for the purposes of getting your final drafted as well. So please do vote. Right now, I'm not going to say if what the exact totals are because people haven't necessarily voted yet. But right now it's on a knife's edge between two of the topics. So really think carefully about what you want to do, and make sure you vote for what you like. If you want to listen to a description more in detail of the topics, I gave that last week in the lecture, and you can check it out on the YouTube channel for the course. All the kind of stuff that comes with YouTube channels. Please pay attention to the uploads, like and subscribe, hit the bell if you want notifications. Sometimes I get emails about that, so I'm not just making a joke there. Definitely hit the bell so that you know when the lecture's posted. So yeah, please do that. And that should be in the most recent one, the lecture that is entitled, what is it? O2, a short introduction to LME4 functions. I believe that I gave that introduction recorded at the end of that lecture. O2 LME introductions. That said, so please do make sure to take that survey. The second thing is, I got confirmation this morning about the scheduling of the final assessment. And the email that I was sent this morning said basically, yeah, scheduling of the final assessments will not change, that it will be exactly what was put on your year-end timetable, or sorry, the sort of semesterly timetable, which, it's not exactly what you want for the outcome, but it's pretty good. So I got that notification this morning, and I posted an announcement at 11:42. 5 minutes after I posted that announcement, the office kit emailed me saying, actually, things will be different. So I just want to let you know that let me just pull it up so I read it exactly correctly. Okay. So, according to my records, the final assessment is going to change from a 72-hour exam to a week, a full calendar week. According to my assessment indicators, that will be released on Thursday the 10th and due the subsequent Thursday the 17th. So this is exactly what I was hoping for, that we could kind of release it a little bit earlier and keep the deadline the same. So that gives you a little bit of extra time. It importantly gives us a Friday to talk about it, and possibly a Thursday if it's released at 10 a.m. So we'll have time to chat about it together, and I'm really excited to do that. But yeah, you'll get a week, which includes the weekend, to work on it if you'd like. I was really nervous about how this would kind of interact with your your Africa essay. Many of you are on this course and Sue's course at the same time, which I think makes a lot of sense. So, you know, if that's you and you're in both of those courses, you'll now have a little bit of extra time and some cushion to deal with that. And I actually think that that one also might get extended too, but I'm not sure. Don't quote me. And I'm also going to reiterate the fact that, you know, even though it's worth 2 times an assignment, it's not going to be twice as long. Okay. So I really think that it's going to be more straightforward than you expect. So you're going to have a whole week, again, the 10th to the 17th. The university, I mean, that's what I've been told. So again, if that changes again, then it's something from faculty or whatever. But that's my understanding as of, you know, 1:15. So as you can see, the situation is evolving. But yeah, it should be a week long from the 10th to the 17th, released, I think, at 10 a.m. and due at 10 a.m. Although I suggested that it was released at 4 p.m. and then due at 4 p.m. But we'll see what happens, actual timing of that. Yeah, and then, you know, we'll see where that goes from there. So that's the good news I have. I hope that that's something that you want to hear. If that really seriously inconveniences you in some way, please let me know as soon as possible. There's nothing I can really do about it because it's the university making these decisions and not me. But it is kind of good to know that that's kind of been solidified. So let's knock that out. Now, the main topic for the lecture today, I don't have anything new to talk about. I just want to talk about some of the questions that people have raised to me privately about the topics in multi-level models. I'd also like to answer questions in the chat if you have them raised. So if there's nothing additional that you want to talk about, I'll get to your question in a second, Georgia. If there's nothing additional you want to talk about related to the exam or things like that, then that's okay. Cool. So Georgia, with the final topic, it's a difficult choice. Yeah, it is. I think that anybody who's choosing visualization because they think it'll be easier might need to recognize that visualization will probably be more programming and less statistics. So if you work in unsupervised learning, you know, I'm going to be teaching you how to use very specific functions and interpret their output. If you go for visualization, you're probably going to have to write more code, but it's going to be visualization code because there's not as much kind of interpretation or things like that there. So I can appreciate that it's a difficult choice, but you will get what you wish for. As I had suggested, my intention was to design the course with a closing module for unsupervised learning. So I'm okay if that's not what people are feeling, but I think you'll find if you intend to go on in data science or are interested in those topics, that unsupervised learning is pretty much half of statistical learning, if not a little bit more than half. In your time at Bristol, we've really only talked about supervised learning. So I don't really think it's more complicated. If anything, it's a little simpler because you're not dealing with kind of like the concepts are pretty simple, and the way that you teach it, you know, is a little bit easier to understand, I think, than some of the things. Like logistic regression is famously difficult for people to grasp. And I can understand that it's challenging. It's something that's important for you to learn, but you know, it's unsupervised learning at its core is generally. So I don't know. It really depends on, I think, what you're interested in, and then we can kind of get there. So I think people may be picking visualization, thinking, yeah, there's less math and less models, but just keep in mind that if we do that, I'm going to be asking you a lot more about visualization theory. I'm sure that you'll do fine. So I would just encourage you to pick based on what sounds interesting in the explanation I gave last week, and then maybe click around in the sources that I've provided to learn a little bit more about the content. So I'll be tabulating the results of that election later today. But I do appreciate that the late breaking precincts need some time to make their decisions. So cool. So what I wanted to do today was just go over some of the concepts and consolidate the questions that I saw in the Blackboard forum, because there are some people that are asking some real excellent questions, and I felt like it would be a little bit not flippant, but sort of useful, more useful if I address these in full across class. So what I'd like to start with, there we go. So there's a couple of really good questions posted by someone that likes to post a whole set of questions all at once about the reading. And I have a feeling that if this person is asking these questions, there's probably a lot of people with similar kinds of wonders. So I'd love to get into this here. So the first thing is about the way that we think of the way that we kind of think of multi-level models and their kind of structure and discussion in the reading. So in section 12.5 in the Gelman, there's this whole discussion of 5 different ways to spell a model. Okay? And by this, he means that there are multiple different kind of expressions that result in the same kind of final model. I'm just going to show you 2, and they're going to be the 2 that we've seen before. Okay? So if I just split here, and I'm going to write one definition on one side and another definition on the other side, you'll see kind of what I'm talking about here. So when we talked initially about the multi-level model, I mentioned that we might have an observation, yi, that is a function of some global intercept, which I generally call A, and then some group level effect, which I was calling U, J, and then some individual error term for person I, which we called EI. Right? Okay. And then for a hierarchical expression, I said UJ is distributed normally with a mean of 0 and a variance of U, sigma squared U. And likewise, I said each individual error is distributed normally with a mean of 0 and a variance of sigma squared E. So this is one way you've seen the multi-level model before. It's just straightforwardly stated in terms of its error terms. This is still the varying intercept model, right? Because if I add these 2 together, I'm going to get my alpha j, but we spell it like this. So in the Gelman framework, this would be referred to as the correlated group error model. Okay, why does he call it that? Well, if we don't know what uj is, and we're only dealing with the terms together as a combined error term, then it's actually the case that uj plus ei together is distributed normally with a mean of 0, but with a really kind of interesting covariance matrix. It's not independent any longer. These things are independent. So they're just a bunch of normal random variables that are distributed according to sigma squared u, yeah? But when you focus on adding them together, these two together are correlated within the group. And generally speaking, it's going to look like sigma squared e plus sigma squared u on the diagonal, or sorry, it's sigma squared e on the diagonal and sigma squared e plus sigma squared u on the off diagonal. The main point is that for the error term uj plus ei, I'm just moving on from that. I don't like that expression because we haven't really dealt with matrices in this, so I'm just going to leave it alone. What I'd rather say is these are correlated with something called the intraclass correlation. So that's U. I'm sorry that that was a little confusing. I decided to abandon that route of explanation because I think it's more confusing to do it that way than it is this way. So those errors together are correlated according to this expression. And this is sometimes called the intraclass correlation coefficient. Whoops. No, just understand it in words. So the main point is that we're specifying two error terms, and they have some kind of correlation when they're added together. Okay? And this is the correlated error perspective on a multi-level model. The other way that you've seen is when you say yi is a function of alpha j plus ei. And then we say alpha j is equal to a plus ui. This is the varying intercept form. It's just stated in terms of its response and then some second level model. That relates how these intercepts are going to vary. This one is modeled as two different random effects, uj and ei. This one is modeled as a individual level model and a group level model. So I'm just going to erase this over here. Call this the error formulation. Now, you can definitely see that substituting this in for alpha j gives us the error formulation of the model. Nothing changes. They're just alternative spellings for how you're expressing combinations of the same values. They're just symbol pushing. That's what Gelman's trying to talk about in chapter 12. Well, 12.5 specifically. He's trying to indicate that there's tons of different ways that you can spell these relationships. I find this one the easiest. Unfortunately, LMER works in this formulation. It's just kind of a cost of doing business. In the case of a multi-level model or a hierarchical model, we use this term. Actually, I'm gonna erase the left-hand side here so that I can have a little bit more space. In multi-level modeling, in the reading and in some of the other stuff, you might see this term, a hyperparameter. This is a parameter, which is just a number or a value. That's all we mean when we say parameter. So it's a number, a parameter that controls the distribution of other parameters. So in this model here, in the varying intercept form, our hyperparameters are A, and then whatever UI, or sorry, this should be UJ. Oops, my bad. And then whatever is governing the group level error term. So the hyperparameters for this model are going to be A and sigma squared U. The parameters are just the error level variation, sigma squared E. Now we think of sigma squared U as a hyperparameter because it governs the shape of the distribution of our group level intercepts. Likewise, this is a mean hyperparameter that governs the distribution of where our group level intercepts are located. But that's all we mean by hyperparameter. It's not really that important to understand what is and is not a hyperparameter, because if I spell this model differently, for instance, if I respell this as A plus UJ, now A is a hyperparameter. Or sorry, A is no longer a hyperparameter. It's just a regular parameter. In addition, U also becomes a regular parameter. Oh, that's going off the edge. So in the correlated error version, everything becomes a parameter. Did the screen sharing seems to have stopped? Can people see changes that I'm making or no? No, okay. Oh shit. Damn it. Okay, cool. Yep, seems like I lost it. No, let me fix it. Sorry, had some kind of drop. Hello. Hey. It seems that the screen sharing broke for some reason. I'm not sure why. So let me try again. Otherwise, I will go back. Odd. One more time. There we are. How unusual. I apologize for that. Just dropped. Your application screen. UX play. Oop, nope. UX play. Are we back in business? Cool. Okay, great. So my main point was just to explain what hyperparameters were and show that, you know, the different ways of spelling the different models, it's just kind of terminology. It's part of the reason why multi-level models are also kind of difficult to understand. In the case of the logistic model, they're difficult because they're nonlinear in terms of what you think about, but linear in terms of something that's really kind of hard to think about. For multi-level models, they're kind of annoying because depending on the way you respell different expressions, they can kind of mean different things. So all I'm talking about here is that hyperparameters are parameters that control the distribution of other parameters. And generally speaking, you talk about a hyperparameter when it's something that you kind of don't estimate directly, and you talk about parameters that are things that you estimate directly. But depending on whose perception of what is direct and what is indirect, you know, we kind of go down these rabbit holes. And if you read the Gelman, you'll see him talk about this in terms of what is fixed and what is random and who's getting to determine that model by model. So this is kind of a rat's nest. So I just suggest that you think about the model in terms of whatever specification makes the most sense, which is either it has two error terms, like we talked about here, or it has that hierarchical structure, which we talked about just a second ago. And either one of those are okay. Of course, when we're dealing with the varying intercept, varying slope model, things get a lot more confusing because you have your outcome being a function of A plus uj plus B plus wj plus ei. And so in this version, this together could be respelled. So if this is your error formulation, you have three error terms, uj, wj, and ei. Seems to have dropped again. Okay, this is not okay. So I'm going to switch quickly back to my other platform. That's a bummer. Okay, if we're back here, then it seems like it's okay. It doesn't seem to have updated though in terms of what it's showing, which is the problem. I need to switch back, I'm sorry, real quick. Hello. Sorry about that. Not ideal. So let me, new movie. There we go. Okay. My apologies. Okay. So this becomes important in the varying slope model, where you might have additional terms that indicate separate components of the model. So you might have this for your intercept and this for your slope. Stated in the varying effect specification, which is, the varying intercept, varying slope, as some might say, we might spell it a little differently and say yi is equal to our alpha that's specific to the group plus our beta that's specific to the group plus an error term for that observation. And then I'm going to set up a hierarchical model that has the group level effect being equal to a group level intercept, a global intercept plus one error term. And then our varying effect, that's gross, make that look a little better. Our varying effect be equal to B plus WJ. Okay, so they're just the same kinds of expressions here, and they're just alternative spellings of the same model. The reason why I like the varying effect expression is because that makes it clear that what we care about are kind of these mixed group level terms, either the slope or the intercept for the group. Okay, so what that question was kind of getting at in the course Blackboard was this distinction. It was sort of this kind of like differences in the way that you can spell the individual components of the model. And I just really want to be clear that that's what Gelman is going for when he's talking about the different ways to spell the model. It's less about them being kind of substantively different and more about them just being the same expression or different expressions of the same conceptual content. So I just wanted to be very clear about that. In the language of LMER, the fixed components of your model in the error formulation are A and B, or A and B down here. And the random components are U and W, or U and W. When you get the coefficient from the model, sometimes called Ran pars, that's actually the combined effect, which here we call alpha j or beta j. Okay? So in LMER, the fixed component is the stuff that applies to everybody, and the random component is the stuff that is varying for the group. The reason why it's called linear mixed effect modeling is because you can get a fixed and a random component in the same term. So you can allow to fit a model that has something like alpha j using LMER. Okay? So I just wanted to make sure that this was discussed because it's a rather important concept in sort of the way that this spelling stuff intersects with the concept of what a hyperparameter is. Hannah asks, does Ranf produce the group coefficients or the group errors? It produces these, the group, oh, whew, not that. It produces these, the group errors. So just to be clear, I'll write this out so you can see it. Fix F gives you back A and B. Ranf gives you back U and, well, UJ and WJ. And coef, which is coefficients, will give you back alpha j and beta j. Okay? So coefficients are like mixed effects. Fix F gives you back only the global, and Ranf gives you back only the group. So when you make the dot plot, if I can move on, is everybody good here? I'll wait a little bit. There we go, some big boops. Okay, so when we talk about a dot plot, and I have a, sorry, let me pop you guys into my speaker. It doesn't show up in the recording. So when we're talking about a coefficient plot, and you're making a dot plot in like the assignment or whatever, your dot plot might look something like this, where you get a point estimate and then a confidence interval around it. And then you might get another point estimate and another confidence interval around it. And then you're going to get a point estimate and another confidence interval around it. And let's just say we get a point estimate and another confidence interval around it. Okay. So normally, in the workbook, I suggest you use something like lattice dot plot on the Ranf. Ooh, that's going to overrun. So I recommend like you build it like this, right? Because it's really simple and straightforward. So what that's doing is showing you uj for every group. And if you remember, uj is distributed normally with a mean of 0 and a variance of sigma squared u. So there's going to be some variation around the point estimate, because there's uncertainty, and then it's also sort of randomly distributed. So it's a random quantity, and we also are estimating it with uncertainty. So there's going to be some error. And what these dot plots are showing you is the 95% confidence interval for each group. Now, why are we plotting U and not alpha? Well, if we were to plot alpha, we would just be replacing the mean of 0 with the mean of A. We're just shifting everything up to A. And the reason why we don't necessarily do this all the time is because A itself is an estimate with some uncertainty. So it's easiest if we just locate it at 0 and talk only about uj. Sophie asks, is uj the group error? Yes. Just like up here when we were talking about our error formulation, I will always be referring to uj as the sort of random or error component of the intercept. And if we talk about the random or error component slope, I'll refer to it as wj. EI is always the error term for the individual observation. Georgia asks, why do we need to use lattice : dot plot when usually you just put the plot, not the package too? Because I don't think I require you to library lattice before that, so I just did it because I didn't want to library the whole package. It's just a way of referring explicitly to the thing inside of the package that you want. Most of the time it should work. And honestly, so most of what I do on a day-to-day basis is in Python. And so in Python, it's much more, it's considered much safer to use this kind of expression where you're kind of saying explicitly, I want the stuff from the lattice package, just in case some other package has defined dot plot. And so like when you load something and you might see R telling you that, you know, it's masking a symbol, if you've ever looked at that warning language when it scrolls by when you library something, that means that two functions have the same name now. And R is going to try and figure out which one to use at the right time, and it's not always perfect. So I like being really explicit about referring to which package the stuff comes from. Finn asks, for a dot plot of beta, is 0 replaced by the B, or is 0 still used? Great question, Finn. So if we were making it of a coefficient, you'd actually, like, say you're doing this exact thing where you're saying the lattice of a dot plot of, you know, Ranf model. And if that model is a varying slope, varying intercept model, you're actually going to get two dot plots. You're going to get one that shows you the u's, which are the random component of the intercept term, and you're going to get another one that shows you the w's. And just like before, it'll be centered on 0. If it were instead centered on B, we would be doing the same thing. B still has some fundamental uncertainty, so it's just easier to show it at 0 and ignore the uncertainty around the global term when we're talking about the group terms. That's kind of the fundamental point of this multi-level modeling approach. You want to get a good estimate of what's global and assign the variability there if you can. And then for each group, you want to get a sense of how variable that group is and get an estimate for that. And you want to separate the uncertainty about the group from the uncertainty about the global estimate. So that's why, by default, this is what you visualize. We're focused on the group level deviations because we just slide them up to B, or in the case of the intercept, we just slide them up to A, and you're done. Great question, Finn. So this is mainly what I wanted to talk about today, was the kind of notions of these different spellings and then a little bit about what the confidence intervals show. Does anybody else have any substantive questions on the material before the due date on Thursday? Anything they want me to re-explain or talk a little bit more about in depth? We got about 10 minutes left, maybe 5. If we put questions on Blackboard between now and Thursday, will they be answered before the due date or in the practical? It's highly unlikely that I will be able to answer them before the practical. I still am behind on your marking this time, so I'm going to be prioritizing from now on to get that marking back to you as quickly as possible. I'm very behind on the marking. So it's just been a crazy kind of couple of weeks. So. Okay, a couple of the questions. Sophie asks, could you go over the random effects in the LMER model outcome? What do they mean? So are you, so on the first question posed, the random effects in the LMER model outcome. So sometimes, let's say if you fit, I think one of the models in the assignment is something like earnings is a function of 1 plus height. And you may have centered height, but I'm just going to write height here, plus height by sex, I think it was. Okay. So if this is the model that we're working with, I might get a result when I look at the sort of tidied output of my model that looks like intercept, height, and then something that might look like SD intercept, and maybe SD height, and then I think SD observation. So go back to our original expression, is equal to A plus UJ plus B plus WJ plus EI. Hannah, yes. Yep, it is, generally speaking. So, the intercept, oops, it's even bigger. The intercept is the A term. Willow, I have height in the model twice because I'm looking for it to be a fixed and a varied effect. If you only put it in the group, it's only going to model the random component. It's not going to try and fit a fixed component. Height there is that. Standard deviation of the intercept is the sigma u parameter. So it's the standard deviation of the random part of the intercept. Rather than giving you directly what uj is, it's giving you that standard deviation. You have to use coef to get the actual mixed part, or you have to use Ranf to get the actual U's. Likewise, SD height is the sigma W that describes the dispersion of the random components of the slope. And finally, the last one, SD observation, is the standard deviation of the residual, E. Okay? A quick one that can easily be answered. When I did a multi-level model, it said boundary singular fit. Does this mean it's wrong? No. Just make sure that you are centering your variables, and if necessary, using a double pipe to say that height and the intercept are independent. Yeah, Isabel, I can. So these ones and that one. Okay? The last question, Neve asks, I'm not sure how to use confidence intervals in question 1.1. I can't really do much with that question other than suggest that confidence intervals, well, I'll leave this up so people can copy it, but I'm not sure what to do with that vague of a question, but confidence intervals, like what you've seen, involve a point estimate, which is this little central part here, and then they add 2 standard errors and subtract 2 standard errors. And these endpoints are considered the ends of what's called an interval estimate, or the confidence interval. So what that generally means is that under a frequentist mode of inference, if you repeat the analysis over and over and over again, 95% of the time, your estimate's going to fall in here if the effect is the same. So if this overlaps 0, what it says is, I can't tell if the point estimate is positive or negative at that confidence level. So if it's the 95% confidence interval, then I could not tell if this point estimate or that estimate is significant. So if this happens, your p-value will be greater than 0.05. Confidence intervals are one-to-one maps to the p-value. The other thing that's useful is that if I have 2 confidence intervals, I can treat them the same as interpreting a confidence interval in 0. If 2 confidence intervals overlap, I can't tell the effects apart. If they're disjoint, if they don't overlap, then the 2 effects are statistically different from one another. So, no, a lot of different things can cause erroneous standard errors. Heteroscedasticity is one of many. It's the main one that we've talked about, and the main one that most people are concerned about, though. Dependence can also cause it. So that's time. I have to run to a separate meeting. So I'm going to cut the question and answer session here. I hope that everybody comes armed with further questions on Thursday. And please, I reiterate, take the topic survey that I circulated before class, and it's also up on the Blackboard, so that your first choice of the last chunk's topic is recorded. I'm going to take the preferences at the end of day today, end of business day, so about 6 o'clock, and rank them based on that. And I'll post all the data along with the algorithm that I do to do the runoff voting if you want to run it for yourself. So cool. I'll see you guys around, and thank you so much for coming. I love it when you have questions, so it's always really good.